Hi everyone, welcome to my channel and welcome to this video. In my previous video, I discussed about what exactly is a file descriptor, how it helps us in accessing file, what is a file description, how they are different, and what is the various file IO related tables that the kernel maintains for us. For example, the per process open file descriptor table, the system-wide file description table or file entry table, and the inode table, right? I also mentioned that once we have opened a file, like once the kernel or once Linux has been able to successfully open a file for us and return us an FD, the kernel doesn't care about the file name or the name of the file or the path of the file anymore, which means we can change the file, we can change the file path, we can move the file to some other location, we can rename the file, nothing matters. Those kind of things should not affect the file IO operations once we have opened the file, right? And I also mentioned that has some very important and interesting implications with respect to file IO operations. So this video will be building on top of that. I'll be kind of extending my previous video, and we will start this video with a very basic question, right? Which more like a situation we might come across in our day-to-day job with Linux operating system. So the question is, let's say a process is actively reading from a file, right? Process is actively reading from a file using its file descriptor, and in this situation, what happens if I go ahead and delete this file from the file system, right? So let's say a process is actively reading from a file, or rather a file is being actively read by some process, or maybe one process or multiple processes, the number doesn't matter. And in such a situation, I go ahead and do a rm-rf on the file itself. What is likely to happen? Will the process crash? Will the kernel panic? Like that's a bit too extreme, but yeah, maybe why not? It can be a possibility, right? Or the other thing is, like, let's say that file from which the process was reading, that has some size, right? Which the size is occupying on the disk. So if I go ahead and delete the file while some process is reading from it, will that size on disk be released? Will that space on disk be released, right? These are the questions to which we will try to find the answers in this video. And so yep, without much further delay, let's get started. Okay, so here I have a very simple and tiny C program, right? And what it's trying to do is pretty much like, there's a function called readFile, and what it does is it first prints the PID of the process. That's the process inside which this program will be running. Then I have a buffer of 1 byte, and then I open a file called t.txt, which doesn't exist yet, but I'm coming to it. So yeah, we try to open a file called t.txt in read-only mode, and then we print the FD of the file, and then we start a loop which continuously reads 1 byte from the file. It prints it out, and it sleeps for 2 seconds, right? That's all that the program does. It opens a file, it reads 1 byte at a time from the file, stores it into a buffer, and reads it and prints it out, right? And what t.txt will be, it will be a pretty big file, something of the sorts of 1 gigabyte. So I don't have much space remaining in my current partition or my current file system where I'm running this, where I will be running this experiment. It's somewhere around 4.8 GB. So if I add a 1 GB file, it will be a noticeable change if I run a df command, right? So the df command basically shows the file system space, file system size on your disk. So we'll come to that soon. And what I plan to do is, when this program will be running, that is, it will continuously read and write to the terminal, I will go ahead and delete the t.txt file, right? And then we will see what happens, how the program reacts, whether it crashes, whether the kernel crashes, if the size on the disk is released, and all those kind of things, right? So yeah, let's do this and let's see what happens. First things first, I first need a file, like a large enough file with random readable data. Like I want to print it on the terminal, so I want a proper text file from which I'll read byte by byte. So I'll do a base 64, and this trick is pretty handy if you ever want to create large files. I'll do a urandom, I'll pipe it out to head -c 1 gig, and I'll redirect it to t.txt. So ideally what it should do is it should read 1 gigabyte worth of data from /dev/urandom, which is supposed to be random, do a base64 on it and redirect it to t.txt. So actually, before doing that, let's just check how much is the space or remaining on my free space remaining on my file system. So I'll do a df-h slash, and if you see right now I have 4.8 gigabytes remaining, right? So I need to work with this. So if I create a 1 GB file, what will be remaining is 3.8 gigabytes. Let's do this. Let me do a ls-lh. So I've got t.txt, which is exactly 1 gigabytes in size. And now if I do a df-h slash, so you can see now the available area in my file system is 3.8 gigabytes. So the file is actually taking up some space, of course 1 gigabytes in space. Okay, so now we have got our setup, we have got the file, and now we can start reading from this file. So let's do that. So I'll clear it up and let me divide the terminal. I'll divide it into, let's say, 3 parts. Okay, and now let's start reading from the file and writing to the terminal. So for that, what I'll simply do is, let me compile it first. And it got compiled. Now let's start the process. Okay, so the PID of the process that got allocated is 34640. Open file descriptor is 3, because we know the first 3 file descriptors 0, 1 and 2 are already taken and by default, and they are assigned, they are used for standard input, standard output and standard error. And you can see that it's reading random characters or bytes from the file which we just generated. And the other thing that we need to remember is the total size of the file system on disk right now is 3.8 gigabytes. So we can also make sure that this file is being, like, t.txt is being read from right now using the procfs. So the 34640 fd. Now if I do ls-lh, so you can see that it's indeed reading from rmfd/t.txt, right? And this is the file descriptor. So now the moment of truth. I am going to do a rm-rf on t.txt, and let's see now what happens once I remove or delete this file, right? So let's do that. Let's verify. The file is gone, but look at this, it's still reading. The process is still able to access the file and it's still able to read it, although the file is gone. Apparently the file is gone because we can't find it in the output of ls, but it's still able to read it. And let's do ls-lh. So here, this is something interesting. It still says 3, and it still points to the file descriptor is still present, and it still points to the correct file t.txt, although it mentions that it's deleted. But the interesting thing, which we will discuss in a while, the interesting thing to be noted here is the file descriptor is still existing. It's not gone from the output of open file descriptors for this process, right? And the other thing that I wanted to now check is the output of df-h slash. Look at that, it's still 3.8ish, 3.7 gigs. Earlier it was 4.8. Our file size is 1 gigabytes, which means the file which we just deleted is still holding space on the disk, which means the contents of the file is not yet deleted, or rather the contents of the file is still present on the disk, and that's why the process is able to read it, right? But the things that we need to also notice that now a separate process, let's say if another process wants to read from the same file, it won't be able to, because the file name is gone from the file system. You cannot find t.txt anymore on the file system. We know it, the contents of the file still exist on the file system, it's holding space, and our existing process which was already reading from it is still able to read from it. The process did not crash, the kernel did not panic, but it's still able to read from it. But the file name is gone from the file listing or file directory and the file system, so no other process or the new process or the same process, if right now if this process would want to reopen the file, it won't be able to do it, right? Because the name is not there. So now we have got our answer to the question with which we started this video. What happens when you delete a file from which a process is currently reading? The answer is any process which was reading actively from that file will continue to get data. This example I showed with read, but this is also true for write. Had this process been writing to the file, and I let's say went ahead and had deleted the file, the effect would have been it would have still been able to write to the file. So that's the ultimate answer to the question with which we started. But now the second question is, why does this happen? Why the process is still able to read from the file which apparently just got deleted from the file system, right? How is this magic happening? And why is the data still present on the disk? Like, why the space that was occupied by the file is not released yet? So before going to answer these questions, these new interesting questions, let's do something else. So right now we know that this is the only process which is actively reading from this file, right? We created this file and this is the only process which is reading from it. What happens if I kill this process? So I'll just go ahead and do a control C. Okay, let's cls-lh now as it is. Now look at that. It's back to 4.80 GB or 4.7 GB, right? It's back to what it was previously. So basically now it was just a moment back, it was 3.7 GB. Although I deleted the file, still it was showing 3.7 GB. And now the moment I kill this process, the entire 1 GB of space got released, and now it's showing that available space on this root file system is 4.7 GB. So which means the space got released back the moment the process was killed. So let's try to understand why this is happening and what's going on under the hood. Okay, so as I mentioned in my previous video, like whenever we open a file, that is whenever we use the open syscall in Linux on a disk file, we get a new entry is created in at least 3 tables in the kernel, right? The first table is the OpenFD table. Let me quickly draw this, it will be easier. And let's say it has got a flags field, and a file pointer field, the one which we are most interested in. And we also discussed that the index of this array, this table is nothing but an array of structs, right? So the index are basically what we call as file descriptors. And then we have another system wide. So this table is per process. Then we have another bigger table, and which is system wide. And again here, let's say among the many columns, one column is the file, or rather field, struct field is actually file offset, status flags, and the inode pointer, very important again. Finally we have the third table, the inode table, where again among the many columns, let's say we have the file type, file locks, and the various other columns. We have the file permissions, then comes the data blocks, and so on and so forth. Whenever we are opening a file, we are getting a FD created here, which points to a particular entry in the file descriptor table, or this is also known as the open file table, and each such rows are called either a file entry or a file description. And here is the inode table, which keeps track of the various inodes in the system. And let's say when we open and we start reading from the file, it creates an offset over here. It stores the status flags, and then it has a inode pointer which points to, let's say, one inode in this table. And this is done for every file, pretty much every file that you read from the disk, right? So this all comes into picture when you have already applied the open system call. The kernel has found out which is the correct inode for the file name. So you are accessing the files by their file names, right? Now the question is, kernel is only interested about the inode to get the actual information of the file, but how does the kernel know when you are trying to open a file by its name, which inode it's pointing to. How does the kernel figure that out? So for that, there comes in another data structure, which is, or another concept in the kernel, which is called a dentry or a directory entry. So the work of this data structure, this dentry, is to create a mapping between a file name and its corresponding inode, right? So that's the work of, that is one of the works of a dentry, to create this mapping. So technically a directory in Linux is nothing but a collection of such dentries. Because what is a directory? A directory is nothing but a collection of files. And if you have a collection of files, the kernel also needs to know what are the inodes corresponding to that collection or list of files. So the directories is nothing but such a collection or such a list of dentry mappings, right, which associates a file name with the inode. So the moment you are trying to open a file by its file name, the kernel will resolve that file name to this inode using this dentry. And there is a dentry cache as well, so this lookup becomes faster when you are doing directory traversing and things like that. So, and this dentry cache is also built as you progress with directory access. But anyways, like, so dentry is the key part here from where the name resolution is done. So once the file has been opened by a process using the open system call, that is, it has done the name resolution from the file name to the inode, and it has the corresponding entries in the open file descriptor table, the open file table has been made, and the link to the inode table has been created. The kernel doesn't need to know, or the kernel doesn't care about the file name or its path on the disk anymore. All it needs is the existing inode, and using that inode it can continue reading and writing, like as long as the file is open. So this brings us to another fundamental question. All this time we have been saying that rm is removing the file. We are using the rm Linux command to delete the file from the file system, right? Then what is rm actually doing under the hood? Isn't it removing the file contents? Isn't it getting rid of the file from the file system? Then why is the inode staying back, right? Because clearly the fact that a process could still read from the file, it means the file contents are still there on the file system. So is the kernel kind of fooling us or something? What is rm doing under the hood? So rm, the system call that rm actually uses under the hood, is called the unlink system call in Linux. What unlink actually does is it removes this file name from the file system hierarchy, right? So all it does is it removes this file name, and it doesn't touch the inode or the file description entry in this table or the file descriptors table. All it does, it simply removes the file name from the file system hierarchy, which means it removes this file name to inode mapping from dentry. What it means is, if another process or program tries to search for this file in the file system, or you apply the find command from the terminal, you won't be able to get the file name anymore. You won't be able to see the file. You won't be able to see the file contents, which means you won't be able to open the file. A new process won't be able to open the file and read from it, but the existing process, which has already opened it, since the kernel doesn't need to know about the file name anymore, once it has opened, it can still operate on the file using the inode. So this is a very fundamental thing of how the remove command works. It doesn't remove the content of the file from the file system, but it only removes the name of the file. So now our question is, when is that actual moment when the actual contents of the file is removed from the system, right? Or rather, the inode, which was looking after the file that we just deleted, is released and it can be reused for some other file. When does that happen? So as and when let's say as and when new processes or the same process using a different open call opens a file, it keeps creating new entries in this file description or file entry table, right? In those file descriptions, the new file descriptions opening the same file will have links to the same inode, right? Now as and when these processes start dying, or these processes start calling the close system call on the file descriptors, what happens is the kernel starts to remove these links one by one, right? So as long as at least one process has still got the file open, there will be at least one link that is still present from the file entry table to the inode table. And not only that, there will be at least one file description. So as and when these links are removed, these file entries are also removed, as and when the process is called the close system call, or the process dies, and the FDs are also released. But as long as there is at least one process which is still having an instance of that file open, and there is at least one link from the file description table to the inode table, the kernel will still hold the inode. It will not delete the inode, right? which means the contents of the file will still be there holding space on the disk. The moment the last process is killed, or the last process calls a close system call on the file descriptor of that particular file, let's say this process also closes it, this file description is also deleted, and the last link gets removed, then what the kernel will do is it keeps a track of the number of links to a particular inode, right? When it sees that the last link to the inode has been deleted and someone has already applied the rm command on that file, right, which means that the kernel sees that all the links to the inode has now been deleted and the file was already marked for deletion, that is the dentry from the file name from the dentry has already been removed. That's the signal that kernel uses to release this inode as well, right? So now the kernel will mark this inode, since it has no more links pointed at it and the underlying file has been marked for deletion. What it will now do is it will mark this inode to be reused, and then when you now create a new file, this inode will be reused to create a new file, and the past contents of the file, the contents of the older file, will be destroyed. So the last link being deleted is the signal, is the actual hard signal for the kernel to get rid of this inode and mark it as reusable for another file, and you lose the content of the older file. So that's how the unlink command works, and how kernel tracks when to actually remove the contents of a file. So as long as you have at least one process keeping the file open, the contents of the file will still be there on the disk and it will still hold space on your disk. So what's the practical implication of it? Well, we have seen enough practical implication. What happens to your disk space is not released, but what kind of problem can you run into due to this? So let's say you're running a web server, let's say you are running an Apache server or engineering server, and you are spitting out the logs to an output file. It's writing all its access logs into a particular file, access logs and error logs. And suddenly at night you get a page that your disk is now reaching its capacity, right? The file has become so long that the disk is reaching its capacity, and if you do not get rid of certain files or you do not free up space, your system will crash because it will have no disk space. So now you do a ncdu or something, or a df, and you find out. So ncdu is a very handy command which tells you, it basically sorts the various directories and stuff by their sizes, and then you can go inside it and see which file is taking more space. So now what you do is you use ncdu, and if you find out that the maximum space is being taken by this log file to which some Apache or Nginx is writing logs constantly, and you decide that your first priority is to save the system, not let the system crash. And what you do is you decide to get rid of the log file, right? Because maybe you are already shipping that log data to, let's say, Elasticsearch or something, so you know that getting rid of the log file is perfectly fine from the disk because you already have the data to rsyslog or something like that. What you do is you do a rm command, you apply the rm command on the log file and get rid of the log file. But the moment you do that, you will run into trouble because you are thinking that it will release the space on the disk, but it will actually not, because Apache is still writing into it. Apache has still got the log file open and it's still writing into the log file, right? Which means inode is still there, the file contents are still there, and if you do a df to check the file system usage, you will still see the same amount of data being held on the disk. That is, the disk space has not freed up. So now you are in trouble, because now, although you have deleted the file thinking that it will reduce the space, it didn't, and Apache is still writing and filling up disk space, because no one is stopping Apache from writing into the log file. The log file is getting larger in size and it's still filling up your disk space. And the only option now you have is to pretty much restart Apache, which might come with other implications, right? Loss of traffic and stuff like that. So this is simply one such example. There are various ways you can fix this problem, but this is one example where you should never delete a file which is being used by some process, right? The reason being, and if the file is open and processes are using it actively, even if you delete the file, your purpose won't be solved. The disk space won't get released and it will still continue to get larger and larger, creating more trouble for you. Yeah, so these are the things I wanted to discuss in this video. What are the implications of deleting a file that a process is already operating on, and how deletion works in reality, how unlink works, how rm works, and what are some of the practical implications of it, right? So yeah, file system in Linux is indeed a very interesting, very interesting and fascinating things, how all these things are maintained by the kernel. And yep, that's it. I believe that's it for this video. Do let me know in the comment section below if you have ever worked with inodes and all these kind of things, what problems you faced, what situations you landed into, and all those kind of things. It's always interesting to hear this kind of stuff. So yeah, this is it for this video. Thank you all for watching, and see you all soon.